life, in my real-time environment. So you can take a picture, you can actually see your sofa being placed in that environment. So that kind of a thing is what we call as augmented reality, right? Similarly, we have virtual reality. Of course, it's completely a virtual space where the person is actually, wearing these headsets and actually gets a feel of, a completely altogether new environment, right? So again, in our CSD, in the Center of System Design at NITK, we have a team who works on this AR, VR developments, game developments, and so on. So again, maybe in the next workshop, probably if we can have it offline, we can have a team who can visit your institution. We can also showcase, the development stages of all these kind of things. Because I assume it's not part of this particular workshop. Here we will be talking specific to virtual labs alone, right? Okay, now let us just go into a bit more technical, aspects of robotic systems, some terminologies which are related to robotic systems, and with this, probably you will understand what are the basic steps involved in developing a robotic system, and with this you can use it for simulating a robot in virtual labs as well. So now let's discuss some of the basic terminologies. One major, now again, if you happen to read journal papers or if you happen to read any technical articles related to robotic systems, one most commonly seen word you observe is pose. Now, what do we mean by this pose? The pose means, now again, in robotics, it is not, especially when we are dealing with a spatial environment, when we are dealing with a spatial environment, defining the position coordinates alone is not enough. Just imagine I have the x, y, and z coordinates. Defining the position coordinates alone is not enough. Now, let's take an example. Just imagine my objective here is I want to use a robot. Okay, I want to use a robot to insert a bulb to the bulb holder. So I believe all of you have done this particular task, right? I want to insert a bulb to a bulb holder. Just imagine I have a LED bulb, and just imagine it's a screw type bulb, for instance. So this screw type bulb, I want to insert it to the bulb holder. So when we are actually doing it manually, what are we actually doing? We are actually orienting that bulb in a certain fashion so that it gets correctly inserted, and then we twist it so that it correctly holds on to the bulb holder. So what are we actually doing there? So what you observe is we are actually basically, what are we doing? We know the position coordinates of that bulb holder, right? We know that it is at, for example, in a three-dimensional space, I know the x, y, and z coordinates of my bulb holder. But if I just randomly take the bulb to that point, will I be able to insert that? It won't be possible because I need to orient that bulb in a certain fashion or in a certain orientation so that I can actually insert the bulb to the bulb holder. So, in layman words, what I mean by poses, it is basically I'm trying to get or represent the position coordinates and the orientation together in a mathematical form. And this mathematical form is what we call as a pose. Now, again, I'll try to make myself avoid the maths here because, again, we won't have time to discuss all those. But I want you to understand next time when you see uh, the pose, you should understand, you should be able to decode what it is. So, how do we mathematically represent the pose? So, it is normally expressed as a 4x4 matrix. So, now again, in journal articles or robotic papers, you will see these kind of 4x4 matrices very common. So, what it is basically is what you see in the last column T1, T2, T3, these are representing the position coordinates basically. That means the x, y, z coordinates, which I already mentioned is known to us. And in addition to that, especially when I'm feeding the robot, I need to correctly feed at what orientation should the robot reach that required position. And that orientation is what we express using this 3x3 matrix here, which I am shown in R, R112, R33. Again, I'm not going into that part of how do we come to this metrics, because there are certain theories which we which we will be learning. Maybe if time permits, next time we can discuss on those aspects, or how to derive the rotation. We call this as a rotation matrix. So this 3 cross 3 matrix is the rotation matrix, and this T1, T2, T3 is a translation matrix. Okay, the position coordinates, and this combined we call it as the transformation matrix. So it's called as a transformation matrix, and we generally call it as the pose of the robotic system. Okay, so I believe you must have got some idea of what is the significance and relevance of representing a point in robotics as a pose matrix. We call this also as the pose matrix, right? Now, the next most commonly seen word. Now, again, as I said, if you eliminate all the motors, the controllers, and electronic components, what it leaves behind is purely a mechanism. So all the concepts of mechanics of machineries and theory of machinery, dynamics of machinery, all those concepts will come into picture. So the first term that we will again more commonly call is the kinematic model. So I believe you know what it is. What is kinematic modeling? So it is basically a relationship between the joint variables and the end effective variables. Okay, now if you just take the case of this robotic system. So this is a robotic arm, as you can see. So the joint variables are what? For example, if this is a, just imagine this is rotating about this axis, rotating about this axis, rotating about this axis. And just imagine I have the end effector at this point. So the position coordinates or the pose of this end effector is determined based on the position of each of these joints. So what I have joint variables. I also have end effector variables. Now this relationship between the joint variables and the end effector variables is what I call as the kinematic model of the system. Okay. Now this kinematic modeling, I can again classify it further into two. One is we call as a forward kinematic model, and the other one we call as the inverse kinematic model. Now what is forward kinematic model? Knowing the joint variables, computing the end effector variables is what we call as the forward kinematic model. I'll come again. Knowing the joint variables, finding what is my end effector variable. That is what forward kinematics is. So that means a mathematical relationship which gives me the end effector variables. So it's basically an equation. So forward kinematic model is an equation which gives me the end effector variables in terms of joint variables. So that is forward kinematics. What is inverse kinematics? It's exactly the opposite. That means in that case, the end effector variables will be known to me, and my objective will be to find the individual joint variables. So it's exactly the opposite. Now, why do we need this forward kinematic model, and why do we need the inverse kinematic model? Now, the forward kinematic model is needed especially during the development phase of my robotic system. That means just imagine I want to know what is the workspace of my robotic system. What is workspace? A collection of points where the end effector can reach. So if that means if I am giving a range of my joint variables, now just imagine for this joint I'm giving a range of 0 to 90 degrees. This joint I'm giving a range of 0 to 45 degrees and so on. For that range, what will be the workspace for my robotic system? That is achieved using forward kinematic model. Now, what is inverse kinematic model? As I said, knowing the end effector variables, finding the joint variables. So when do I need that? The inverse kinematic model is needed, especially for the control purpose. Control purpose means, just imagine, I want to use my robot for spot welding operations. So if I'm using my robot for spot welding, what does it imply? I know where my robot, where the end effector should reach. So indirectly, I'm knowing my end effector variables. So in order to reach that point, what should be the respective joint variables? Because I control my end effector variable using my joint variables. So in order to reach a particular pose for my end effector, I should be knowing in what fashion each of the joint variables should be moved. And that is done using the inverse kinematic model. So forward kinematics is used for the development and optimization purposes. So just imagine my objective is to optimize the workspace. So what should be the optimal joint variables and so on. Similarly, link dimensions. So this kinematic model will be in terms of joint variables, link dimensions or dimensional parameters, and end effector variables. It's basically a relationship between these three. So I can do optimization and all these kind of analysis using forward kinematic model. And also for controlling my end effector, I need the inverse kinematic model. Okay. Now the next important model we have is the dynamic model. So now if you observe in forward kinematic model, there is no effect of joint forces or joint torque coming into picture. Now just imagine I want to develop a robot to lift 10 kgs load. So if I want to lift this 10 kgs load, I should have the motors connected such a way that it can, with, for example, just imagine as a human, if I want to lift 10 kgs load, I need to have the muscle power to lift that much of load, right? Similar to that in robotic systems, I need to fit in with the necessary motors at each joints so that I can lift so much of load. So that calculation is done using the dynamic model, right? Again, dynamic, there is forward dynamics as well as inverse dynamics. I believe you can assume what it is basically by now. And there are different approaches where we can get the dynamic model for systems, which you must have already studied in your school physics. Like, for example, methods like the Newton-Euler approach, the Euler-Lagrangian approach, virtual work principle, Hamiltonian. So there are different ways by which we can get the dynamic model for the systems and so on, right? So when we try to incorporate the effect of joint forces and joint torques, then it comes into the dynamic model of the system. And then we have the degrees of freedom. So this I believe you already know. It refers to the number of independent ways by which the robot can move, right? So for example, now just imagine if I want to use this as a robotic system. So this is a 4-bar mechanism, right? So this 4-bar mechanism, all the links are connected. So there is only one way that this system, this mechanism can move. So this is can be categorized as a one DOF system and so on. Okay. And workspace I have already mentioned. So now just imagine this is a robot. So it's a collection of the points that the robotic system can reach. So this we have already discussed. So this is how the pose matrix will look like. So we have a 3x3 representing the orientation. So there are again different representations. I'm not going into those aspects as of now. Maybe in our next discussion we can discuss those things. Similarly, the P represents the position matrix. So these things are normally we take it as zeros. So this eta, it refers to in what angle are we actually viewing. So normally we try to model a robot viewing it orthographic. So that means we are viewing it at an 90 degrees or normal to the robotic system. So if we are viewing the robot from a perspective angle, these will take some other values. So as a robot developer, we normally keep it as zeros. We normally model the robot viewing it orthographic. Okay. Now, if we are a computer graphics person, will if they want to view it in some other perspective, then maybe they take it as non-zero values, right? And this is the magnification factor sigma. So 1. So this is the collection of what we call as a pose matrix, right? So again, as I said, so now just quickly because I've already taken more than an hour, so I'll just quickly wind up. So I'll just show you. So now by now you must have understood what is meant by forward kinematics and inverse kinematics and so on. So let's take this forward kinematics of a Puma 560 robot. So it is a well-known industrial robot, right? I'm directly going into the simulation. So this is how the Puma 560 robot looks like, right? So now just imagine. So this is the pose matrix as you can see. So it is modeled with respect to the base frame. So I'm just changing. For now, you can see as I change this, as I change these parameters, you can see accordingly the transformation matrix is also changing. So the position coordinates change as well as the orientation change. Again, as I said, for now, just understand this as rotation metrics. I am not explaining what are these values or what are the significance because that will take that altogether is a nearly 1 hour lecture. So I believe maybe we can have that discussion later. But this position coordinates thing is very straightforward because you can relate what it is. It's basically trying to get me the position coordinates of my end effector with respect to the uh, base frame or the global frame. Similarly, if I'm plotting the workspace, you can see. So this is the workspace. It's a collection of the end effector variables, as you can observe. So I have given some different ranges. For this range I am analyzing what is the workspace. So these things are very much required, especially during the design phase of my robotic system. So if my objective is, I have some specific task, and I know what should be the works, what should be the pathway. So what should be the optimal dimension? So I can do these optimizations and all these kind of analysis using these mathematical models. So in the background, what happens is, it's basically those calculations which are happening in the background in order to give us these values, right? Okay. Anyways, uh, uh, as I said, there are a couple of other things also to discuss, but I'm planning to stop with this for now. So maybe we can have some questions if there are. Hello.
Yes, sir. Yes, sir.
Yes. So I because I've already taken more than the time. So if I keep on going, there are a lot to discuss. So maybe I believe I've given some fundamentals of how to understand robotic systems and how we can relate this with virtual labs.
Yes, sir.
Can we have some questions, if in case you have? Yeah. Thank you. Thanks a lot for the support. Yeah. If
Thank
I
you.
need to design model a robot for hearing impaired, what I should do? If I need to design model a robot for hearing impaired, uh, can you give me more clarity on what you mean by that for hearing impaired? So if okay, see if that is, if you're talking about the feedback mechanism. So again, see, I've actually got involved in a project where I tried to get involved with developing uh, a smart. Okay, I think I have that with me. I'll just show it to you. Yeah. So can you see this picture here? This one. So this is basically a cost-effective assistive mechanism visually impaired. So it is not only for visually impaired, visually as also for uh, those people with hearing difficulties. So what we have done is, we have actually given a haptic feedback to the uh, to the uh, to the handle, so that, just imagine, so see, basically those people who are blind, uh, and who are also at the same time, just imagine they are deaf and also they are blind, both of them. So normally those people, you can see, they either use a conventional cane or a stick just to hit around and walk, just to see if there are any obstacles, or they use an animal or a dog probably, which will guide them to walk around places. So what we have tried to do is, we try to develop a smart stick which has, now just imagine the person is both blind and at the same time he's deaf also. So in case an obstacle comes, we give this haptic feedback. So this haptic feedback means it will give some kind of vibration to the handle, stating that there is some obstacle coming in the coming towards you. So the person will get an understanding, okay, there's an obstacle coming there. Okay. Similarly, if the person is only blind, what we can do is we can give audio feedback. So it can actually give. So it has necessary sensors, camera basically. It can, for example, if it is given that, that means if we can train the machine learning algorithm, so to detect certain people or certain faces or certain objects, it can actually give that audio feedback. So in case a person is deaf also, we can give haptic feedback. So based on vibrations, they will understand what it is and whether there's an obstacle. And if the obstacle is coming very fast, we can increase the frequency of that vibrations and so on. So these are some ways by which we can give some assistance to people who are having hearing disabilities, and also audio feedback, yeah, or blind issues, right? So hearing impaired. So I believe I have answered your question.
Yes, sir. I have raised the question. Thank you for the presentation, sir.
Yeah.
Sir, already robotic arm is being developed by people, sir, for supporting the hearing impaired and vocally mute people.
Okay.
Is there any room for developing the same, because robotic arm is not that much flexible on making the signs for interpreting or establishing communication between hearing impaired and normal people, sir. I hope you may aware of sign language.
Correct.
Sir, if I tend to make the same robotic arm by using a soft robot, as you have mentioned in the slide, are there any research or going, sir, in the same field?
So
Or any
you are
other software I need to use?
no, you mean to say you want to use a soft robotic gripper for hand signs. Is that what
Yes,
you're
sir.
trying to tell?
Yes, yes, yes.
Yeah. See, actually, you can actually there are not exactly, but you can use these soft grippers with pneumatic systems. So it has the 5 fingers, as you can observe, and you depending on which finger, because hand signs involves certain motions and it needs to be at a very faster pace. So you can think about using some soft silicon rubber based material with provision for the air to move in through. So depending on the suction and expansion, closing and unclosing, what happens is the each finger can be actuated, and also the gripper can be actuated depending on the motion that we need. So you can actually design it as such, if you get me.
Right, sir. Right, sir. Sir, if all these materials are biocompatible, sir.
Which one? You're talking
The
about the smart
material which is
material.
used for soft robots. Yes, sir. Yes.
See, there are different materials as such you can observe. As I said, see, it also depends on the application. So in certain cases, it might be piezoelectric where we give some external force which causes or maybe if we give some electric signals, it gives some actuation forces. But the problem with those materials is that the amount of actuation that you actually get is very limited. So especially with this biocompatible materials, and also talking about the ionic polymer composites, so all these things do give us actuations, but it is very minimal, or compared to a pneumatic system, it is very small. So for your application, what I suggest is you can think about a pneumatic hand gripper. You will find several research. Even I have a research paper, but it is mainly used for some other application. So my purpose of developing the gripper was to handle delicate objects, delicate system, so that it does not crush the delicate object as such. So maybe what you can think about is you can think about redesigning your gripper, which will look more or less like a human arm, and maybe you can actually control each pipeline of your finger, so that depending on which finger to be closed or to be open, accordingly you can actually actuate it. It is possible. It is a doable work.
Already I have developed a hand glove along with the flux sensors, accelerometers, sir.
Okay.
For while they are doing science, it will be automatically detected, and embedded controller will say what is the sign made. But the
Excellent.
thing is
Okay.
that recording the accuracy and precision, I hope it is not fully satisfied. So in case of robotic arm, it can be easily handled by the people and the accuracy will be more. For that only I'm asking this.
No, robotic arm, you mean to say, is no, I'm just trying to understand your problem. Do we need the full robotic arm for this hand signal, or
Yes,
is it
sir.
enough? Is it enough to have the gripper part only?
No, up to the, even if it is possible, up to with the elbow.
You
From the
need it till
finger.
the elbow, right?
Yeah, yeah, sir.
Okay. Till the elbow. Uh, and you prefer to have it rigid, is what you're trying to tell me,
Yes, sir.
instead of a soft.
Yes, sir. If I want to design a soft robot, sir, will virtual lab supports the complete
No, as of now, this virtual lab is not having the module for soft robotics. It is still in the development stage.
modeling, sir, soft robot.
Hello.
Hello, sir.
Yeah.
Am I audible?
No, as of now, are you thinking of using a conventional robotic arm for this purpose? Is that what you're asking?
Yes, sir.
Okay. For that, you can get the kinematics direct from what is, as I said, in that module, you have, for example, I'll just show you. Sorry. Sorry for all these things. See, for example, just imagine I'm thinking of using the KGP robot. Just imagine this is the kind of, okay, let's not make it this complex. Let's go for the move master. Yeah. Just imagine you want to use this kind of a robotic system for your purpose. So what you will have to design is you will have this arm which will be fitted to the uh, stationary base, and then you will also have a gripper which will be a soft gripper, because I believe the 5 fingers needs to be independently controlled, right?
Yes, sir.
Yeah. So what you need to do is the kinematics for this part, you need not redo it once again because it's already developed. You can directly take it from this virtual labs. For example, depending on which is the motion you want, accordingly, you can actually control. You'll get the kinematics, you'll get the workspace plot. So that much of information you can take from virtual labs. But for the end effector part alone, you will have to manually do, because that module is not there presently in our virtual labs for the gripper part alone.
Yes, sir. Yes, sir. Understood.
So that part you will have to, again, as I said, it is one of the proposal which we have already given from NITK. Probably in future you can see that module to come maybe, but as of now we do not have that module for soft materials or soft grippers, because one thing is because the maths involved is entirely different for a soft material compared to rigid mechanisms, as you can observe here, right? So until this point, that means until your end effector, until you reach your end effector, you can model using this virtual labs, but this part alone you'll have to simulate it separate, the gripper part alone, because in this we have
Yes, sir.
only this much of motions possible. This gripper portion is not included there, right?
Similarly, sir, the gripper is having only 2 points to carry some things. If I want to have the 5 fingers to be simulated, can I do, sir, with the virtual lab?
That is
Even
what I
if
said.
it was-
That is what I was mentioning. So as of now, in the present module, it is all the robots that you observe. Now this is the move master. Similarly, if you observe the case of the Puma robot also, everything is designed for a, you can observe in this case also. You can see that the gripper which is taken is, so it is designed for a, it is a claw mechanism. It's a what do you say, 2-fingered and effective gripper.
It's maybe used for pick and place purpose.
They see, this is designed for purely pick and place operations, but your application is you need all the 5 fingers for your
Yeah,
application.
sir. Yeah,
So
yeah,
that is what I'm saying. So you can make use of all the kinematics till this point.
Okay, sir.
You can take all the workspace, kinematics, even dynamics you can take up, but for the end effector part alone, you'll have to simulate it separately, because that is a 5, that your end effect, your finger alone is going to be a 5 DOF system.
Yeah, sir.
So in that case, it will be altogether the end effector alone you will have to simulate separate, but all
Yes,
the
sir.
others you can take up from this virtual labs.
Thank you, sir. Thank you.
Yeah, thank you. Yeah, there are multiple ways to have joint angles. Is there any method to optimize? See, that's what I said. See, here the kinematic modeling, the formulation part we do is mainly to do this optimization. So you'll have joint variables as well as your link dimensions. Everything will be variables in that case. And our objective, for example, if I want to get, my objective is to maximize the workspace. For this maximum workspace, what should be the link dimensions? So we have learned that in mathematics, right? So that comes in the development phase of my robotic system, where I'll try different combinations and do the maximization or minimization problem in order to get to the optimal link dimensions. So that is what we basically do. So optimization is a part of. So again, when we are developing a robotic manipulator, again, those who have studied kinematics of machinery must have already studied something which is called as synthesis of mechanisms or mechanism synthesis. So what is mechanism synthesis? Basically, it involves 3 steps: the type synthesis, number synthesis, dimensional synthesis. So all these synthesis has to do something with the optimization also. So in type synthesis, we choose what is the configuration of the mechanism and so on. Again, I have not discussed the various configurations of robotic systems. Again, if time permits, we can discuss those things. Okay. Then similarly, number synthesis means we choose what are the number of links, what are the number of joints needed for the mechanism. Then in dimensional synthesis, there we do the optimization. What should be the optimal dimensions for a particular objective function? So all these things comes in the synthesis of my mechanism, which is the first step, because only after the design is complete, then only can we go to the controller design and the choice of actuators and so on. Because from the dynamic model, we choose what should be the motors required in order to support the payloads, right? Similarly, for the controller, for example, if I am designing a force-based controller, I need my dynamic model to be incorporated because that's a prerequisite. Because without the dynamic model, without the effect of inertia, without knowing the effect of the gravity, without knowing the effect of Coriolis and so on, I won't be able to design my controllers. So those are all the prerequisites. So the development of robotic systems always begins from this mathematical modeling of our system. And once that is complete, then we go to the next stage of designing controllers and so on, right? So I believe I have answered your question for that. In case of fitting a lamp as example, there are multiple. Yeah. Okay. Now again, just take the case of a robotic system. So when we are defining constraints, all these constraints will actually reduce the chances of multiple solutions. Now if I want to reach this point, I can reach like this. I can also reach like this, the same point, right? So I can actually define some constraints for each joint. So again, while controlling, we have those constraints well defined, because for a particular constraint and for a particular same point, there is only one possible orientation for that reaching that point. Okay. So that is where we actually define these, you know, limits for each joint while it moves, right? I hope you have got the answer.
Yes, sir.
Okay, attendance is not with me, please. Yeah. Thank you. Yeah. If there are no more questions, then maybe we can, uh, uh, are there any more questions? So, anyways, thank you for the positive feedbacks. So, again, as I said, this topic that we are discussing is a very vast. It's a very vast topic. So, it's not possible to complete everything in maybe 1 hour. So, what I try to do is just give you some understanding of some technical terminologies that we normally use in robotic system developments. Maybe once you get these, so now when you read some articles related to robot development, you'll get some more clarity. Because once this is done, the next phase is to think about incorporating AI, machine learning, reinforcement learning. So you keep keep adding, or keep add-ons to the robotic development system. So anyway, the first step is what we are doing right now. The first step is to develop the mechanism synthesis part, or the mechanism part, right? So anyways, thank you very much. So anyways, we look forward. So I request all of you to make use of this platform. So not just for robotics now. The reason why I chose robotics is because that is my domain of work. But I request all of you to make use of this virtual labs in any course that you take, because there are different different domains available in virtual labs. So in case you are dealing with any of the subjects, even for engineering graphics also, we have platforms made in virtual labs for you. So please make use of these platforms. And in case you have any concerns, or if in case you want to do some online or offline workshops specific to certain domains, you please contact us. So either you can write a mail directly to me, because I'm also the Institute Outreach Coordinator for Virtual Labs. And I also request you to please talk about virtual labs with other institutions as well. And in case they are not a nodal center of any institute, please tell them what are the benefits of being a nodal center with us. And you can encourage them being with us, right? So I'm winding up with this for now. So thank you very much for all of you for your patience and support. Thank you.
Sir. Thank you very much, sir, for this wonderful session on how you can use virtual labs to teach robotics to the students. and also giving us the basic fundamentals of robotics for all of us. So thank you once again, Mavinja Thomas sir, for this session. I also
Thank you.
thank, yes, sir, thank you. I also thank Professor K.V. Gangadharan sir for the first session that he has taken on introduction on Virtual Labs initiative. I thank sir as well. With this, we have come to the end of the first session, first day, and tomorrow we'll be joining back tomorrow, and then our team at NIT Suratkal would be giving a demonstration of the virtual labs for a specific area of computer and information science and allied domains. That's for tomorrow, and all the faculty who are into computer sciences and information sciences and all the allied domains, you can join tomorrow and make use of this opportunity. With that said, the attendance link will be posted in the group. Yes, we'll be posting it now. As I speak, they'll be posting it. So kindly fill the form. Yes, it's already posted in the chat box. So kindly fill the feedback form. And if you have any questions, you have an option over there to write your questions so that we can get back to the team and then clarify whatever questions you have. Ma'am, Shrestha ma'am, anything that you want to share?
No, sir. I think most of the points are already covered, and we can discuss further on virtual labs in the upcoming days with the domain-specific sessions. And the form for any institute to become nodal center, that is expression of interest form, I have shared in the chat box as well. So if any of the faculty from any of the other colleges want to be part of virtual lab as a nodal center, they can fill the form and mail to solve at NITK. I'll write the mail ID as well, so they can send a scanned copy of that particular expression of interest form. Yes. So other than that, I don't think any other points, sir. So thank you, Marvin, sir. Thank you, Gangadharan, sir, for today's
just
session.
want to add one more thing. So please, all those who are not nodal centers, so please make use of this platform. So it's a completely free platform. So you just need to sign this document which Shrestha has shared in the link. And once you are a part of our nodal center, we can organize these kind of workshops to your institute as well. And that too, please note, it's taken, the expenses are taken by the Ministry of Education. So please make use of these platforms. Our objective here is to maximize knowledge sharing, and also we can have, again, both offline as well as online. So the first step for this is to be a part of our nodal centers. So please show your interest, and you can connect with the mail ID given, solve@nitk.edu.in, or else maybe you can directly write a mail to me as well, mervinthomas@nitk.edu.in. So you can find any of these details online as well. So once again, thanking each of you for your patience and support. Yep.
Thank you, sir.
Thank you very much. Thank you, ma'am.
Thank you, sir.
Thank you everyone for joining today. We'll see you tomorrow for the second day session on the demonstration of the virtual labs. Thank you. Have a great day. Thank you. Please fill the feedback link, which is posted in the chat box.
And just a communication, sir, as discussed previously. So day 3 session would be demonstration on virtual labs in circuit domain and physical sciences.
Yes, ma'am. Yes.
Yes,
We'll tell them tomorrow so that they'll remember.
Yeah.
Yes, ma'am. Thank you. Thank you, everybody. Have a great day.
Sir, any link is shared for attendance? I hope I have submitted the feedback form.
Yes, ma'am. The feedback form and attendance both are the same. That's
Oh, fine. Yes. Fine, sir. Fine. Thank you.